In this video, we'll talk about direct bandgap semiconductor versus indirect bandgap semiconductor. There is a diagram which helps us understand this concept very well, and that diagram is called the EK diagram. And E we know is the electron energy, and K is something that we are seeing for the first time in this course. And I can assure you this will be the last time you'll be seeing the K. So K is actually called the wave vector, or it is called propagation constant as well. Now, the discussion about K itself is beyond the scope of this course, so let's not worry about what K is. But the way I would like you to understand K is something that is related to momentum. For direct bandgap semiconductors, the EK diagram would look like this, where E is in Y direction and K is in X direction. And the graph would look like this. And this is for conduction band and this is for valence band. And the lowest of this conduction band to the highest of this valence band is called the energy band gap. And I'm reminding you that this is actually not plotted with respect to X, the distance. This is completely different. This is called EK diagram, where energy is plotted with respect to wave vector or propagation constant. For our understanding, we are just taking K to be something related to momentum. This is how it looks for an indirect bandgap semiconductor. The EK diagram, where the lowest point of the conduction band to highest point of valence band is called the energy bandgap EG. And x-axis we have taken a wave vector, and in y-axis we have the electron energy. We know very well about recombination, where we have electron from conduction band combining with a hole in valence band, and this process is called recombination. Let us see how does the recombination happen in direct bandgap semiconductor, and then we'll compare with indirect bandgap semiconductor. We will see the difference. Basically, the difference is in terms of the recombination of carriers itself. So now let's say we have an electron at the bottom edge of the conduction band, and let's say there is a vacant state at the top of the valence band. Now, when there is a recombination happening, basically it should satisfy the conservative laws. And one of it is when electron combines with the hole, one thing is the energy should be conserved. In the sense, when it actually comes and recombines with the hole, the amount of energy that it actually loses should be resulting in something else. So that something else is usually a photon which is of energy h nu, where nu is the frequency. Now if you see here, the energy is conserved because the amount of energy it has lost is actually given as light with energy h nu, and the amount of energy would be equal to the energy difference between the energy level of electron and the energy level of the vacant state hole. So that would be equal to this h nu. Now, when this electron transitioned into this state and filled it, the energy is conserved, and at the same time, we have talked about that K is related to something called momentum. And in general, momentum should also be conserved. But in this case, if you see, the electron and hole are actually matching with respect to the momentum. Basically, the momentum is also conserved. So that's why when it actually recombines, it actually gives rise to a photon. And now, why did we consider only the electrons at the bottom edge of conduction band combining with the top edge of valence band empty states? Is because let's say we have an electron at top of somewhere in conduction band. Now, electron has a tendency of coming to lower energy level. And because there are a lot of energy levels present in conduction band, it would slowly come down to the most possible lowest energy level. And then it cannot go to any other energy level other than actually coming to valence band, unless we give additional energy to go above. But in general, it comes to valence band. So the probability of electrons actually coming from the bottom edge of the conduction band to valence band is higher. So that's why we talked about this situation. In direct bandgap semiconductors, the recombination of electron with the hole will result in a photon of energy h nu. In case of an indirect bandgap semiconductor, let me take an electron here, and let me take empty state present at valence band. Now, if this electron has to recombine with this vacant state in valence band, then there should be conservation of energy as well as momentum. And now if we observe here, momentum for electron and momentum for hole are different. So how can they recombine? Unless the electron loses momentum exactly equal to the difference between these two and then recombines to actually give rise to energy. This is very highly unlikely situation unless there is assistance for this electron to do so. Electron can lose this momentum if it interacts with the phonon, where phonon is the vibration of atoms in the crystal lattice. When it interacts with the phonon, it can lose the momentum, so it can pretty much, with the momentum lost, it can recombine with the hole in the valence band. But this even is a very highly unlikely thing to happen, which means the probability of happening this is very less. So in order to assist and accelerate this process, usually we'll assume that there is an intermediate state introduced because of dislocations in the crystal, which means the crystal is not perfect, or intentionally introduced energy states in the energy band gap to decrease the carrier lifetime, so that this will assist the electron to actually lose the momentum and energy at the same time and come to this intermediate energy state and then recombine with the hole in the valence band. In general, in indirect bandgap semiconductors, the recombination is non-radiative in nature. In the sense, it usually results in heat, whereas in direct bandgap semiconductors, the recombination is usually radiative in nature. So when we talk about devices which emit light, we choose direct bandgap semiconductors. Example of a direct bandgap semiconductor is gallium arsenide, which is a compound semiconductor. And example for an indirect bandgap semiconductor is silicon and germanium.